and it's a pleasure to introduce our guest today, our guest speaker. Professor Hava Siegelmann is an internationally known professor of computer science and a recognized expert in neural networks. She is a core member of the Neuroscience and Behavior Program and director of the Biology-Inspired Neural and Dynamical Systems (BINDS) lab at the University of Massachusetts, Amherst, to be exact. She is particularly known for her groundbreaking work in computing beyond the Turing limit and for achieving advanced learning capabilities through a new type of artificial intelligence called lifelong machine learning, lifelong learning in particular. Siegelmann conducts high interdisciplinary research in next-generation machine learning, neural networks, and intelligent machine-human collaboration, computational studies of the brain, with application to AI, data science, and high-tech industry. She's a leader in increasing awareness of ethical AI and in supporting minorities and women in AI and STEM fields all over the world. Siegelmann has been a visiting professor at MIT, Harvard, the Weizmann Institute, ETH, the Salk Institute, Mathematical Science Research Institute at Berkeley, and the Newton Institute at Cambridge. Her list of awards includes the Obama Presidential Brain Initiative Award, the Donald O. Hebb Award of the International Neural Network Society for contribution to biological learning. She was named the Distinguished Lecturer of the IEEE Computational Intelligence Society. She's a fellow of IEEE, of both the IEEE and the International Neural Network Society, INNS. Please join me in welcoming Professor Siegelmann.
Thank you so much. What a nice introduction. I'll come every day. Okay, so thank you very much. I'm having a great visit so far, so thank you. Okay, so we'd like to talk about intelligent, robust autonomy and about a few ways that you can try to reach it. So for the inspiration, we can look on all kind of application which are related to computer games and to visual identification of objects. And it seems that AI is doing so well, kind of better than human. And at the same time, you take the same basic engine AI to the outside world, and sometimes it's not even trustworthy. And this discrepancy is really weird. And I think that one of the chief reasons for that is that AI, and it doesn't matter if it's the classical AI or it's machine learning, it's frozen once it's ready. So just for the people outside of the field, if we have some, we mainly have two types of AI. One which is programmed, so we put programs if fever is more than 38, then you test or something like that. So this is something that was written by a programmer. Another way to train AI is to provide a large database to give a network or a neural network, to give a training algorithm, and then this training algorithm will work on your data set and will fit all the parameters in the network. And once the network is in, this is equivalent to the program. So this training of machine learning, what it cuts to you on the ability to understand what the expert knows. It just gives you a lot of example of what the expert does, and the network will fit the parameter to work kind of like the expert. Either way, if we programmed it, or if we gave a data set and ask the network to fit its own parameter, either way, once the training is over, everything is frozen, and now the AI is ready, it's in the world, and it has to start working. Now, naturally, when it starts working, if it's, in a situation like that, if this is the time and this is performance, so during training, we always see performances like that. They're going up. That's what training is doing. After training is over, if it's frozen, it can never do better than what it was doing. However, it can meet with some conditions that it's too far from what it was trained on, and it will crash. So what we would like to do is to talk about lifelong learning AI, and what we would like to have is to have the network aware of what it does and how the situation is, and taking it in a positive way so it can continue to learn forward. So in short, what we have in systems that are not lifelong learning, we have no way to prepare the training set to cover every eventuality. And they're also, because of that, there are malfunctions in unseen circumstances. And the last thing is it's also easier to attack system that doesn't change. So if we think about the possibility of we need to have some safety or security, like in medical applications, then it will be a problem if the system doesn't change. So for all this reason, we want to talk about lifelong learning. So some of you know I served in DARPA in the United States for some time. I'm not there anymore. I left about 2 years ago, and everything they ask always to say that everything that they say has nothing anymore to do with what the US government wants to do. So totally out back to university. So the way that we wanted, we kind of define a program that was called lifelong learning. And this was like one of the largest, richest program in AI ever. And we had a few pillars that we wanted to cover. And I'll introduce you just the main of them. The first one is the notion of continual learning. So we want to expand our knowledge. We don't want to rely solely on the training set. It's good to start, but we want to continue training more. The second thing that we want to have are internal explorations. So internal explorations are, you want to know more than the data that is given to you. You want to ask yourself, what if I was doing this? But you don't want to actually do that. Like, what if I close my eyes and cross the road? So you better try it in internal exploration to see what kind of outcome can be, so you don't have to do that outside. And by doing internal exploration, you kind of know better yourself, know better the environment, and try things out. I'll give you examples of all that. And this is really important for safety-minded system. Another property that is very important is context-modulated computation. And here the notion is that you can learn something in general, like how to play a particular game, but then you want to modulate it, not just for speed for another person, but you want also to change rules. And you don't want to train every time from the beginning. You want to do like very smooth transfer without many changes by some way of modulation. And all these features are important because we want to get new models, new behaviors, new capabilities. And that's what we really want to get when we're talking about that. So what I thought to do is just to talk with you a little bit about each of them, so we can see what's the situation, where the field is. It's good. Oh, sorry. Okay. So I want first to talk about learning more over time, or expanding your knowledge. So let me introduce to you first the notion of a continual learning. So in continual learning, you learn the first task to do. And then when you're done, you learn the second task to do. And people started working on this, I think, in 2016 already. And they call it task incremental learning. So you learn first to separate between 0 and 1. And when you're done, you learn how to separate between 2 and 3. So this kind of makes sense that there will be such a feature for neural network, but there is a very strange feature. After you think about it, it's not as strange anymore, that is called catastrophic forgetting. So what happened in catastrophic forgetting, let's say that you learn to separate the 0, 1, and you know it very well. Now you give examples to the network, the same network, and you try to teach it to separate between 2s and 3s. So what will happen, you will separate very well between 2s and 3s, and you may totally forget catastrophically 0 to 1 separation. So this is what is showing here. So you learn the second task, that's the accuracy, and the first task is being done. And this is really horrible, because if you're talking about things like self-driving car, you know, they worked for months in all kind of simulations, and they have billions of examples. Now you want to train it after one accident, and you know how to handle now this particular angle of flight, but you may forget everything else. So because of that, there are a bunch of people and a bunch of companies started with Google DeepMind and Stanford that suggested various algorithms that will push this further and allow you to add a few tasks. So in this example here, we have 5 tasks. And if you don't do anything, then the average goes down, because every time you forget more and more of the previous one. And if you do this one, it worked. So they showed a few of them, but they seem to have a problem. So the problem is this. If I learn 0, 1, and I learn 2, 3, and I learn 4, 5, okay, I learn these 5 tasks continually. And now I'm not a robot, you know, I want to separate between 8 and 4, or between 7 and 5. So with all this algorithm, it's not just a regular neural network that you cannot combine tasks. All this method actually make it impossible to combine tasks. That's how they remember. They remember so well, and they learn something else in another part and make sure that there is totally no overlap. So they make sure that there will be no overlap. And so currently, all these methods now are doing, when we want to combine, they're doing that. So we call that class incremental learning. So it's really understanding more about the class, not only about the task. So understanding about how to combine things, more basic understanding. And we would like lifelong learning to have something that allows us not to forget and also to use our experience. And that's actually most important for the notion of lifelong learning, because the notion is that it's not that somebody teaches you all the time, but you yourself go through life and you have more experience. And you don't want to do exactly like that. You want to combine something that you learn in first grade, maybe how to read, and something that you learn in 12th grade, maybe something about math, and something that you learned 1 minute ago. So you want to be able to combine that. So that's kind of the basic for that. So the basic continual learning will not do that. And I showed just one option of a working. And this is a joint work with Guido and Andreas. And the notion is this. You can take all your, let's say, 0, 1, and 2, 3s for this simple example. So let's say that we come with a new task to learn. If you were remembering everything that you had before, kind of like in a database, and then retraining everything again. So when you train the 2, 3, you will train again the 0, 1, it will work. It's not very scalable. It's not very energy efficient. But this is this is what is called retraining. Thank you. There is another idea, and this idea is generative replay. And the idea here is you may not remember all the data of 0, 1, because you don't have it, but you created a generator. And this generator will generate previous data as you learn new data so you can combine. So this is a great idea. There are some problems which are practicals, like, I don't know if you have a lot of experience with guns, but they have amazing papers and amazing videos on them, and sometimes you're really lucky and you succeed, and then you can write the paper, and usually you're not lucky because in guns you have to have two networks that have to go exactly at the same time with small difference, everything break. So it's not really working very well. People love it because it looks to them like dreams, and you generate data and then put the dream data inside the memory, and we love it very much in neuroscience to talk about it, but it doesn't work. So the idea that we suggested here is not to have a separate generator, but to have one network. And what the one network will do, it will not generate all the way to the input, because that's what is so hard to do. Like generating all the way to the input, it will have to have a person that looks like a person. But it will generate only a little bit. So it will generate to high abstraction. So from that high abstraction, you can continue learn, and it takes also less time. It's very, very easy. So the pictures will look something like that, very, very bad pictures, but we don't care because this is kind of abstraction of pictures. And between that, you get much, much better results. So to clarify, the problem of catastrophic forgetting is not totally solved by that. I think I and my colleague think that we have an idea of why catastrophic forgetting is here in network and how to handle it by changing basic notions of neural network. But as long as we work with something very similar to the type of neural network we have, it will be a problem. So I want to talk about internal exploration. So internal exploration, for example, on the left, you see this hand, and it has to do task, and the gray shaded image is the internal understanding of the hand about itself. and it tried to learn itself. And only once it's more or less learned itself, it doesn't have to be perfect. Once it understands itself, it can start working. And you see this a lot in babies, kind of how they do all kind of random things. And once they get how it works, it works. And the beautiful thing about this type of internal exploration for robotics is that you can change now the outside of the inside, and the system will learn very fast. So the relearning for the new things will be very easy if you already have some internal demonstration. So this was in Science Robotics in 21, and Hod Lipson is the main person. And another example, this is in the vision area of internal exploration. Let's say that you saw lots of images, and many of them don't have label, or so you can either get a lot of images without labels, or perhaps you try to reuse things that you have. So instead of having only 100 images, you want to make them into 1,000 images by using the same images. So you can ask yourself a question that you will know the answer, that you can take this image and take this piece out and hiding it from yourself and say what was supposed to be here. Or you can look here and say, is it this color make sense or some other color? Another thing, you can take a large image, you can take a piece, which will be the reference image, and then take all kind of parts from various images you saw, and one of it is from that. And by the time you start training yourself, that there is some correlation between something like a train and something like a train station, you learn something new. So it really starts teaching you correlation of how things together. So the internal explorations have very large goal in making the maximum understanding from what you have. So within the same lifelong learning, we had a bunch of biologists, and they continue working in all kind of crazy ideas, where part of the robot is real and part of the robot is a tissue. So these guys from Tufts University, they're kind of designing robots in the computer and then make them from frog skin. It's actually really interesting because the frog skin robots actually do a lot of things. They start having social behavior, and you can use them as sensors. It's really very interesting, a whole field by itself. And I just want kind of to end that part and say that when you test for lifelong learning, it's a mistake to work on the same ImageNet and the same data set, because the whole point is not to have fixed data set. So you can take, for example, this is from Stanford Research Institute. So you can, for example, take a game and start changing the terrain, altering unit capability, move the goals around, maybe increase even the weapon range or move friends to foes, stuff like that. So when you do that, you see if the system is fast enough, if aware enough to see that something is not right, and trying very, very fast to try other things to do. So that's the feature of lifelong learning that we want, is to have this extra safety, that something doesn't work as we wanted, and I'm close to find how. So I wanted to put like 5 minutes for theory. In heart, I'm still theoretician. And to ask why in AI we're talking about these systems that don't change with time, that kind of freeze after they're taught. You know, it reminds me of my son when he was in 2nd grade, and he told me that he's smart enough. Everybody tells him that he's smart. He stopped learning. At Christmas time, he said he does not want to go back to school. He didn't like the people there. They're really not nice to him. You know, he was short with big glasses. But he said that he's smart enough. You know, the teachers tell him whatever, that he can go to university. So he took it seriously, and you know, so this is kind of a little bit like regular AI in that sense. It's like you learn until middle of 2nd grade from your training data, and you don't continue. So the question is why we do that. And I think that one of the main reasons we do it is one is really the really hard technical issue like the catastrophic forgetting or others that are actually really true. But the other reason I think is because of Alan Turing, this genius that did the Turing machine for us. And the whole notion of the Turing machine was that you can have a universal machine, a universal mathematical model that has, you know, tape and has some general part. And when you load the program in, this general machine will go one line at a time on the program, and it actually will activate your program. So you need just one machine. You don't need a machine for every program. Just one machine, you load the program and it does it. So that's why it's really it's so genius. And that's why it works for a general understanding of computer. I always tell my students this was kind of his undergrad thesis. So when people ask me what level I expect from them for honors thesis, I say, let me just think of one that comes to mind. So because of that, we have the programs and rules, which is the loadable program, or we have the machine learning that will provide the data set and we learn parameters. And the parameters can be, like in neural nets, we don't know what they mean, but we still train them. But so it's still kind of like in between. It's less trained than it's kind of like we know less than when we write a loadable program, but it's still frozen. So there are other ways to think about computation. And the one that I like to mention is the super Turing computation. And super Turing computation is, from the mathematical point of view, it's really a continuum of hierarchies. It's a continuum of computational power, starting at the Turing machine and going up all the way until it's stuck. So it doesn't go to tautology. It goes to some machine that we call, some level that we call it super Turing. And there are various ways to gain it. So one way to gain it is changing, instead of working on discrete or bits like in a digital computer, we can think about real values, or physical values in the outside. So it's really kind of taking the machine a step towards nature. So we can do that. Another option, we can take a deterministic computation and take it to involve some randomness or some asynchronicity, or we can take a pre-program and instead of pre-program, allow it to evolve over time, kind of in the lifelong learning. There's another way that is very interesting. You can take a Turing machine and every so often change to another Turing machine. And the notion is that if at any point of time you're working with the Turing machine, but the whole sequence, the whole process is super Turing. If you didn't know in advance how you will change it. So in fact, there is the simplest one. You can take two Turing machines and change between them based on inputs, and that's also enough to take you to the hierarchy. So, it's a continuum hierarchy, but maybe one of the interesting points here is that the central model of the Turing machine becomes here, for the super Turing, it becomes a new central model, and this is analog recurrent neural net. So it's, we have the nodes, which are the neurons, we have the connection, which are with the weights on them, we have input and output, and as long as it's recurrent and the values in the neurons don't have to be just binary, then any of the features written here will make it stronger and stronger along the hierarchy. So this is just kind of something that is generally interesting. And just to give credit to Turing, so Turing wasn't a fool, so when he introduced the Turing machine, he was very clear that he's not trying to do an intelligent machine. And he also was very clear that he was looking for an intelligent machine. And in fact, he was looking for a few methods to do that. And I didn't know that actually until something like 5 years ago. So I was very surprised and I was almost sorry that I didn't know that. So he suggests various ways to do that. He said we can use the bits of the pipe. So he's talking about moving from Q to R, from rational to real. He brought to his work in London, he brought a supply of radium and wanted to work with that together with the first computer that they had, because he wanted to have true randomness. Or he's talking he's not writing, but he has lots of his speeches. That's why I didn't know about them. That he's talking about learning from experience. And the way he talks about learning from experience, when you listen to that, it is from experience. He's not talking about training set. So I found it like a few years ago, and I thought it's really interesting, these features, because he was really looking for strong AI. I just came from the mathematical point of view. My PhD is in mathematical view. I just asked what's the computational power of recurrent neural network. That was the question, because it's so different. But it's interesting that there is some, that you get this and it's some commonality. So I want to go back. Do you have any question or any comment? Okay, so I want to go back kind of like to the general view of how to get AI to be intelligently and robust. And we talked about lifelong learning. Some robustness is about robustness that is related to adversarial attacks. There is some robustness that can come from understanding of time rather than just vision, but a good understanding of time. And there is another way, which is combine humans still with the AI in a way that one person to a lot of AI in a way that makes sense. I tell you, a way that doesn't make sense is Tesla cars that you can drive without looking at the road, and then when the car doesn't know what to do, it wakes you up. And then you're in a situation and you have to solve it. So that's kind of an example of what we don't want. Okay, so I will just talk very shortly on each of them. So in general, the deception against AI is a really cool idea. The idea is to take the strength of the AI and use this strength, which is what we call the superhuman capabilities, take exactly this strength and go exactly there. So in that way, the human will not notice, but the AI that has its own way of understanding will be failing for that. So for example, we know that the neural network will understand that one as this animal just because it has the same feature. So they kind of look a lot about the texture. And if it is given this image on the right here, it looks kind of like my cat meal. And this one looks more like an elephant. And the machine decides that this is much more an elephant than it is a cat. So that's kind of the power. So if you want to take that, for example, forward, we can say, okay, if you want to have texture, let me give you the texture from that, and let's see if I can fail you. So that's kind of like a cool way of failing. Another way is, you put these tiny things, and because AI is so good, our eyes cannot see them, but the AI will capture it. So this is a little example that I did. I did it when I was in DARPA, and they begged me not to publish it in paper, was to take, this type of images and put very, very small little cute cows on them. And the machine tell us that it's a group of cows because these cows even go towards us. So that's another, we take this power of this kind of addition that, is known that, we can trick the system. And that's another one that I really like. So this is a person that doesn't exist, but let's call him Bill. And Bill is interested in Wonder Woman, and you can understand why. I would be also if I were a man. So his trick is that he cannot enter a club of all the Wonder people because he's just a regular human being. So what he does, he figure out any accessory. And what he does, he takes lots of pictures of Wonder Woman and took this accessory, perhaps in different size, perhaps in different angle. So slowly the machine started understanding that these new images that are hair, and it's clear that it's hair, has something with the glasses that is very, very important feature. Then you take this out. I just left it a little bit so you see. So instead of giving this, it gives kind of like images that in the eye we don't see very clearly that we added. We added to the training data. We can just put it online. And then our Mr. Beale put the glasses on, and voila, the system tells that he's Wonder Woman and he can enter the club. Very easy. Everybody can do that. You don't have to buy anything, to eat anything, to drink anything. You get any accessory you have at home and you play that in the internet. Very easy. So this is a whole field, about how to guarantee AI against deceptions. And this was actually my second large program when I worked at DARPA. So I just want to tell you just kind of basic things. Explainability does not help against deception. So that's kind of, many people say, if I have my AI explain how it came to the decision, it will tell me, this is an elephant and not a cat, and it will tell me why, then I can handle it. But in reality, it's so easy to trick explanation that you don't even want to get there if you have a system that is it can be tricky. Computer confidence, I think all of us know in AI that the network does not do a very good job in computing confidences. Okay, so I'm going to go back to adversarial in just a little bit after we start talking about time. Because in fact, I realized that with time-aware model, you actually have more capabilities, not only for accuracy, but it's also more robust. So this is my current research. What I've talked now is nothing is being published yet, so you cannot find it out yet. Please don't publish it before my students do. I have 3 students working on that and part of the dissertation. Okay, so let's start with just kind of general thinking. So let's say that we have a neural network or an AI, and I'm asking it, will I have traffic on the way home? And if the AI doesn't understand about time, it says, yes, if you drive on Route 91, you have 72% to have traffic. Your answer is 72%. So this is the system doesn't understand anything about the time. If it's a little bit smarter system, it will say, well, now it's 10 in the morning. Your chances are only 30% that you'll have traffic. But if it's even smarter, it will also look at the day of the week and say it's Friday at 10 o'clock. You'll have 50%. But then it's even smarter if it looks at the calendar and it says it's Black Friday. This is a big shopping day in the United States. Everybody outside. It's not a good day to go out. A few years ago, I was stuck in traffic for pretty much the Black Friday in traffic. So it's not a good time to go. So if a machine that will do that will be much better in prediction. It will not need just to summarize in very general knowledge. It will actually understand the temporal features. And here you can actually use it for understanding changes in sky. So there is a second way that we want to think about. So one way is really kind of to talk about timing prediction, like to predict what's going next. The second one is time in action. And time in action, when to hit the ball. Okay, so you have a system, it's kind of a reinforcement learning, robotics, it needs to know when to do things. Or if you can do things in a particular time, it may be different. Maybe if the ball is here, I will hit it here, and maybe if I caught it here, I need to hit it a little bit differently. So the timing will make you different answers. And then, you cannot talk to me without having some theoretical tools. My heart always go there about how to talk about it. So I want actually to start with the second one, which is time in action. So in general, in real-time setting, it's very crucial to understand why doesn't it play? Okay, it's very crucial to understand when to do things and to do them very fast. Something this fast is very crucial, even if it's not good. Like if you have a robot that lost footing, you first want it to walk forward, even without noticing details. Or if you have this pendulum that kind of plays with that, it's not real. It's a simulation, what you call. So you want it to, you want to move it and to do things, even if they're not perfect, sometimes. And you want to be able to answer differently in different times. Okay. So what happened actually in real-time reinforcement learning? So in general, reinforcement learning is that kind of notion. You're in a particular state, and then your machine is taking an action, and then you're in the next state, and you make another action. So if you note the time that I gave to the states, I gave them actually some time. Because by the time you decided here you look at the action and you decided to move it. So here you decide to have, to do A1, but it takes some time from your decision. It took you some time to make the calculation, and then it takes you some time from the end of the calculation until you actually started it. So in current state-of-the-art approaches in RL, we assume very strong computers. So if you have very, very strong computers, they're so much faster than the environment, it doesn't really matter. The calculation time is nothing, and the time to act is nothing. However, if you work in other type of computers, they're more like the brain or more like cheap type of sensors, they're working far from the cloud. So then ones that are energy-minded and smaller, you still want to work it well, even that it takes time. And the only way to do that is by using some kind of prediction. So, my student work on this prediction and how to work with the system that change over time. And one of his findings is actually very interesting, which is when you work with RL, it's regular or the one that is time aware. It's not always better to go to smaller cuts of time, because when you work on smaller cuts of time, it means that you have to calculate more because there are more things to learn. And you add more things to learn, you have more issues, not just the power, but also you can start occurring mistakes. So you really want it to be not too fast, not too small time, and not too slow, because then you'll fail and you miss the point. So it seems like that the time slicing or the time reaction is actually very, very crucial. And one of the work that we do now is to talk about adaptive or predictive time rates that we change. And I found it recently. I thought it's very cute. They tell you something that we also found in the simulation, that if you want to fit so if you see they move a little bit differently. So the notion here that the environment force and the mass of the object that move in it changing the way that they move and the way that their time slicing is. So this is very interesting, because we also found that as we change the environment, what we call gravity, and when we change the pendulum's mass, we needed something very different. So I kind of found it interesting. And another thing that he's doing, he's adding reflexes. So what does reflexes give you? So here he just added few neurons. And what reflex give you is that you can work in particular time steps most of the time, but sometimes when you have something that you cannot rely on prediction, you still have a chance that the environment will do something very bad and very fast. So reflex help you for these things. And something that is currently being learned. So this was for time in action. I want to talk a little bit for time prediction. And you can think of a time prediction in the following way. Let's say that there is a particular behavior during the day and particular behavior during the night. So in general, if you want to explain the behavior, it will be, the state space here will be of 12. Or you can take only 3 and change how they go, modulated by what versus its day or time. So you may take very small state space and explain it in a temporal parameter. So that's kind of what it can give you. So Adam, my student, call it templates. And the notion is that you will change the parameter of the network over time. And you actually learn these patterns. So kind of like we learn pattern in vision, we'll learn pattern in time and use them. And this is just an example of one of its results. You can go, once you change to templates, you can have much less parameters. In this example, you can go to 5,000 from 1 million. So when you make a change like that, there is no comparison for the power and actually also the accuracy, which is very interesting. So I'll tell you in general how it works. So the idea is that he takes a recurrent neural network, and instead of weights, instead of learning weights, he learned effective weights or weight function. So the weight function has the weight and the t. Okay, so he learns weight and how they change over time. So this, he can put it in a recurrent network. He can also put it in neural ODE. So neural ODE has this very nice feature that you don't need to get input in every discrete time. And because of that, if you get input once in a big time, you're not wasting anything. In general, the way that the neural ODE work, you have, this is kind of the recurrent neural network part, but you're not moving with fixed time. You're moving to the next one when there is more input. And meanwhile, you integrate from the last time. So you combine an ODE solver together with RNN that moves to the next step just with input. And it gives you great capabilities for input that come only once in a long time or things like that. And the very general idea is this learning of the function, the weight function, and the one so far tried is based on the Kuramoto model. But you really can try various, various other functions. Kuramoto had some nice features, but I'm sure there are many others that we haven't learned yet. And if we think about the network changing like that over time or periodically, we can think as if we have like a bunch of neural network that we change them, and then maybe we repeat them and repeat them, based on what we learned the period is. So just some results, there are some great sepsis and mortalities. Also, there is human activity that we can do with much smaller parameters, much less epochs and better, and also the physics Juko database. The interesting part here, I think, is the main notion is to look at 50 body position and generate the next 50. It's kind of a prediction, but you can also take only 5. So it has this capability with the neural OD and temporal, which is really, really powerful. So a comment here. So this type of machine learning has this feature that seems so far that it's much stronger to adversarial attacks. And you can actually understand why. We end up with a very small network. Small network is much harder to trick. Also, there is understanding of something about what's happening in the next time step. So if something doesn't make sense now, you already have expectation, which is pretty good, you have good prediction. When you have a good prediction, you can counter yourself. Okay, and the last part is just some theoretical tool, and I'll tell you what it is. It's really easy to understand. So let's say that I have just 3 states. It's kind of like a finite state automata, and let's say that during the night I move by whenever I get A, I move to 1, and whenever I get B, I move to 3, and whenever I get C, I move to 2. And let's say that that's what it does in the day. So you can see that the A ones are the same day and night. So we put them here, and we will call it time-independent behavior because we act on the A the same way. But for B and C, we have time-dependent behavior. Okay, so general temporal automata will give you this feature that some, and then we write it together as one, just as this say in this writing. So this is the automata. It will tell you that at daylight it will work like that, and at night it works like that. And if you want to think about how the data looks, so the data looks, it will give you the symbols as an input. Sometimes it will not give you input. It's okay, because we're in ODEs, we don't need input always. But so we can get input, A is sometimes you get B, sometimes you get C. And this is the way that we get the states. We were in state 1, and then we got symbol C, and we moved to state 2. Now I shaded here so that you will see the day and night, but the network does not see the day and night. It has to figure out that there is another process there just from the data. And there is some feature that I found very interesting that Peter found. What he found is that if you only train only what symbol that A does, or if you just train a finite automata, you do that immediately very, very well, because it's very easy to understand the time-independent variable. But what he showed actually, that if you learn something like this, you will learn very fast the first parameter, or the parameter that are time-independent, then it will take you a long time. That looks as if the network does nothing, and then it will understand all and jump. And actually, when you look at the details of what it's doing when it does nothing, you start seeing that it start creating waves. It actually, in the moment that it understood that there is something about waves, something that is periodic, something that is changing, it captures all the other inputs. It's kind of like a new concept that it needed to get in, and once in, that's it. So I just kind of find it very interesting, and he's trying to work with for lifelong learning now. So this is kind of like I put for summary discussion. So we talked a little bit about lifelong learning, which is the feature that will give us a little bit more. We talk a little bit about adversarial issues, and adversarial issues are not relevant just for army. I mean, this is wrong. It's actually more relevant on our privacy, on our medical data. If you were insulin pump, you don't want somebody else to start activating it for you from far. So all these things are important. The time awareness is what I'm currently doing, and it's really better understanding of the environment, better prediction, better comprehension in a small way, and human in the loop for another time. Just the notion of how we can include and it still makes sense. So that's it. I think that I would like to suggest that perhaps in a few years, what we call today AI maybe not consider as intelligence unless we add to that lifelong learning, some good prediction, and maybe even timely response of what to answer.
Thank you. Questions?
About the TFA?
Yeah.
Because we say that you showed some states. What if, and on the slide it said finite number of states in that state space model. What if we have finite, but there are so many in number? So many. There are so many factors affecting the.
Yeah. So a good question. So the way that we define the TFA is like a general way. We have, states and symbols, and we move there. And the reason that we define it is in order to be able to define complexity classes. So now you can take this TFA and make it harder in different ways. One way is to add more states or to add more symbols. Or instead of just changing one, you can change hierarchically, like day and week. So you can have like hierarchical features. So the reason that it's interesting to define that and then to move complexity is now we actually take various different existing recurrent neural networks like transformed neuron or others, and try to see what they're working on. And it's interesting to see that each of them is more sensitive to different complexity. So some are hard when it has a lot of nodes. Others find it hard when you have hierarchy of temporal features. So once there is this, we can pull and push it to different directions to define complexity hierarchy on which we say, because if you look at data, people tell me, I have that and I can do it, no problem. And then we take it to TFA and say, well, this is TFA of 2 states. Your data is fancy, it's fMRI, brain data. For the temporal point of view, it's not really that exciting. So that kind of allows us to take type of data and to say where they come in this complexity, and then to see what's happening with them. Good question.
Kartik, you have a question?
Yeah. Hi, Professor Hava. Thanks for the nice talk. I have one question. So basically, one of your arguments is lifelong learning or continual learning will improve the trustworthiness of AI systems, right? But the problem is, when you continuously try to learn, you might also learn the wrong things, right?
Yeah.
So just like
so
human
this
beings, we kind of get influenced by many, whatever we call as misinformation, disinformation.
Yeah.
Anything can happen.
Yeah. So once you learn, you can learn all kinds of things, and that's why in the type of lifelong learning, you always have check and balances in different places. And the nice things about it, that's how it's built. It's built to be all the time self-aware and to see how it's doing. So in general, it should be kind of like you try to design it in a way that it will, let's say that it's in a car, and you try to teach it to open up also for the last 10 minutes so it will be more aware of what's now. Mm-hmm. And it's true that it has different way of deception and different way of safety, which are part of the field's understanding of study. But I wouldn't say that they're easier or harder than others. So when it comes to deception or doing wrong thing, it's kind of like have their own features. They still have the feature that they're aware and they update and they don't forget. They put things together, and many times they can be there. So one of the reasons sometimes that you want to have the human in the loop is related to safety and security.
Yeah, I think human in the loop is really important for these kind of problems, because otherwise you can easily poison the environment or the data and make the system try to learn the wrong things.
Yeah, so yeah, you need its own thing. Also note that once you have a various awareness, so temporal is one, once you have kind of also prediction and understanding, and you predict and you see that you need to train on, or you need to open up, then also it's when you have to put your care and focus. Yeah, but good question.
Yeah, thank you.
Thank you, Kurt. Thank you, Kurt. Tim?
So from the perspective of NLP, there's sort of perhaps not enough talk about, but increasing awareness, I guess, the importance of temporal shift in our models. So for sentiment analysis, say, if you trained a movie review system on reviews pre-2000, and they saw the name Robert De Niro, they'd probably say, great, this is going to be a good movie. And post-2000, they would say, crap, this is going to be awful. But unless you're sort of doing some continual learning to update the model all the time, as well as you have some sort of temporal variables so that you can map it to the particular time point. So given that this was a review for a pre-2000 movie with Robert De Niro, it's probably a decent movie. But because this is posted, so yeah, for the same model, rather than just sort of having a static
That's
model.
interesting. So given the age of the
Yeah, exactly. So what you said about continual learning versus some temporal shift versus sort of self-supervision or weak supervision, which has some supervision signal somehow. How do these things all sort of meld together, or what are the connections?
So I think that they have the same goals, but under different assumption of what you have. So if you have like a stamp on the data, you have something that is very natural. Then your question is aging, and you know that it's from 2001 and 2000, and you can even decide that everything from before 88 is less relevant from 2000 and balance the data. So this is something that comes in the data. Many times I think about understanding the environment is something that does not come to me with the data exactly, but I just start to find the pattern. So I don't know here that now it's more relevant than every 15 minutes, and again now, and again. So something like this. I think that the temporal awareness is more like finding things that are not clear from the setting.
Right.
For continual learning, so continual learning can be good enough in all kinds of things. So the question is again, what's your assumption of the data?
Mm-hmm.
So if it's a well-behaving data, you have enough all the time, and it's labeled well, then you can deal with less sophisticated mechanisms.
Yeah.
And I think the goals are the same. It's just the question of the situation. Like, can I deal with what I have, or do I need to go to another effort?
Yeah. You can ask a follow-up question or
No.
be brief.
Later. Any other? Okay.
I want to ask you about your opinion about using still just like models like transformers and continual learning. Like the result of continual learning is like try to mimic the human ways that human learns. So we try to use memory, we just try to discuss for our previous knowledge. But transformers in particular are not really learning like humans, but they are proving to be
They're
very
really good.
Yeah.
Yeah. So one of my students, Joshua, is actually worked with transformer to try to do temporal features. In particular, what he tried to do is he tried to identify in the picture that they had day and night, and if you identify that they're day and night, it's a bit smaller. It's interesting with the transformer, it can do some particular complexity very well, and particular complexities cannot. It actually breaks very low for others. So it's very interesting. Also LSTM, because LSTM I think was my first to go. So the whole project started at first where we had a problem and we started with LSTM, and it can't fail that fast, and all its claim to fail is that capability.
Yeah.
And then the transformer can do something very well and some other things not. So I think just kind of adding more also the way that we think about changing weights. So the changing weights are working for any network. So if you do changing weight, you can do changing weight. For LSTM, you can do changing weights for the transformer. So it's kind of a general idea.
So in continuing learning, as a follow-up, in continuing learning, have you reached a solution for the catastrophe?
No.
Not yet.
We,
The transformer then?
okay, so
No?
so none of them can handle catastrophic forgetting. In order to solve catastrophic forgetting, what I believe is you need to add other features to neural networks, and I'll come in demand to give you the second. You just need to change some features. I'll tell you why. I think you kind of will be able to think about it. If all your memory is in one layer, and then whatever you write in one form and one layer, then whenever you write another weight, or never update weight, you lost what it was there before, because it's on one layer and there is no something that will help you to get it back. So as long as it's flat memory, you will have catastrophic forgetting. The question is when. So like the generative replay is still the winner from current approaches, but I am very good at showing you how it fails. And then we need something else. We need to think differently about memory.
Could you put his hand up?
Kun, you have a question?
Oh, yeah. Thank you, Martin. And thank you very much, Professor Hava. So actually, sorry, I missed the first part because I had to attend another meeting. Probably you already discussed this issue. If you would like to go back to the summary, it will be great. So essentially, you summarize the 4 points, right? And seeing that
now
the first
I know
one,
when you joined us.
Yeah, nice. So seeing the first one and the first one, third one are kind of related, right? Because both of them are about how you can just go, but as time goes on, right? How you can react, right? The first one is the lifelong learning, and the third one, not third one, the last one. The first one, last one are somehow related, right? Because you have
sorry, the order, the order. Oh, sorry, I gave you the wrong order. Okay.
Yeah.
Now
perfect.
You
okay.
order.
Thank you. Now I'm
I
more
had to
confident.
change my previous talk, so this was from another one. Yeah.
Wonderful. So here, would you like to explain how basically lifelong learning is different from online learning? Because in lifelong learning, you are supposed to have a way to accumulate and store your knowledge, and you are supposed to, as time goes on, you are supposed to expand your knowledge, right? So it's still slightly different from online learning. Could you please say a bit more about it? Essentially, as time goes on, you want to be smarter and smarter, right? You have a kind of more and more complete understanding of the environment. So how can you achieve that?
Yeah, so first, we don't achieve that yet. It's a topic, kind of like AI. We don't have it yet, but we have some. So in lifelong learning, the main thing that we try to have is not to rely on training set and not to rely like a parrot on previous experience. Should I talk louder? Like that, it's better?
Oh, wonderful.
Okay. So in lifelong learning, you don't want to copy what you had, but you want to combine information from what you had. And one of the features that we talk here was internal simulations, that you take all kinds of things together and do a lot of if then, what would happen if I do that. So you try, we think about the process as not an input-output process, but it's a whole system process that you work when you have data, and you work even harder when you don't have data. So in general, in lifelong learning, the goal is to be able to have this capability to say, I want to combine something from last year, from 2 years ago, and from 5 minutes ago, and I want to combine them as a way of a solution. So to come with this kind of creativity of putting things together, that's kind of the main feature that we want from lifelong learning. So it's a little bit different from continual. In continual, you have to come up with one. You have to say, yeah, that counts exactly what I learned 5 years ago. I'm going to copy that here and work. So it's kind of the combination.
Oh, cool. And basically, you are saying that we cannot store all the data, right? However, we still have a way to learn and organize knowledge. This way, we can do learning. So essentially, how can you represent such knowledge? And then how can you make, right? Then if you can represent such knowledge later, you can just make it better, right? So in what way do you think we can store such knowledge that we can discover from previous data?
Yeah, so part of internal simulation, which I didn't talk much about, so part of it is to come with a way of finding various features and store information in a few places with different type of indexing, or a different way of taking it in and putting it out. And the internal part of what internal simulation is sharing different representations for the same stories. And then when you use it, you frequently want to use based on one feature space, and you go to there, and when you update everywhere. But the updating of the space.
Thank you. One last question, Tim.
Or I can ask offline if you have time.
No.
So we're looking at sort of structured models, but coming back to the temporal question, capturing things like periodic events, periodicity, or events which are associated with other events, structure within your observations to kind of predict the fact that something's going to happen, preemptively adjust your model. Have you looked at that at all, or do you have any thoughts about how to do that?
I'm not sure that I understand your question, so let me try to repeat it.
Yeah.
So if you ask how we identify that there's a particular period.
So, one could be periodicity if you like your night and day sort of thing. And can you, so it's a very simple instance, I guess, of periodicity. Maybe it's more like weekends, or the behavior is different on weekends, or once a year events like your Black Friday.
So these are hard questions. And what we try now is to, we're working on that, so it's kind of work in progress. But as a work in progress, we try to have so a good temporal automata would be one that gives you the minimal description to explain the data, allow modulation. So let's say, now and in the next day, you can modulate because it's your second day in something. But as long as you can explain, that's the goal. It's very hard to reach, optimality. And what we try to do is we try to go with more features. So what we have in the current state of the art is basic periodicity, basic modularity you can find. So like the type of example that I showed very fast from medical data, you find some periodicity in the person. That's why you can condense a lot of medical prediction. To go to hierarchies, we're working on that. We don't have a good solution so far. I can tell you the ones that need to work. But we usually don't do that in the top, but I can tell you the various methods that we try not to work yet. We have various ideas, but these are really hard questions because the individual, I think we'll never get like the optimal. It's kind of like we cannot even do optimal finite automata, but this is even harder. But try to attack it from, it's very hard.
All right, let's thank the speaker again. Thank you very much.
Thank you very much.
Thank you.